Question 2, the first thing says what's meant by an excited atom, and your answer for that has got to involve the words electrons, energy level, ground state. The next part says describe the process by which mercury atoms become excited in a fluorescent tube. So you've got to mention that you've got electrons travelling along the tube, they're the current coming from the terminals. Then you have to explain how they collide with atoms and they give energy to the atoms, and then say what happens in the atom to make it excited, relating to the energy that's come from the collision. What's the purpose of the coating? Well, this is in your textbook, it's on page 37 of the main textbook. If you remember, the mercury atoms have given out ultraviolet photons, which of course will be useless alike because we can't see them, but when those ultraviolet photons hit the coating on the glass, they're absorbed by the atoms, causing the atoms to be excited, and then when the atom's been excited in the coating, instead of going straight back to the ground state, which will give out an ultraviolet photon just like when it's absorbed, it goes down in two stages, and you get two photons that have got less energy and therefore are in the visible part of the spectrum. So you get 3 marks for explaining that clearly. The next part of the question is 2b, or perhaps it isn't. So it shows the energy levels, and it does say it's not to scale. Now when you get these diagrams, it's always useful to have a quick check of the units, and we notice that this gives the energy in joules, which makes life easier for us. Other questions might be in electron volts, so you've got to be prepared, if it is in electron volts, to convert to joules. But this we don't need to. And it does say the diagram is not to scale. Usually when it says the diagram is not to scale, it means they just haven't bothered to draw it particularly carefully. Here, I think they've actually deliberately tried to be unhelpful. So if we look at these differences, the difference between minus 0.26 and minus 0.59, what's that, 0.33, and that's shown as quite a big gap. The difference between 0.59 and 0.88, well that's almost 0.3. Looks much smaller. So let's make sure that we're not going to get caught out by things looking different from what they actually are. So part 1, calculate the frequency of a photon due to the transition from 4 to 3. So if an electron's going from there to there, we can work out the difference between the energy levels, and we don't worry about the minus signs, we just get the difference, because we know that this energy is coming out anyway. So when we work out how much energy the electron will have to get rid of to go from 4 to 3, we know that that much energy will be the energy of the photon, and if we remember the equation that links the energy and the frequency of a photon, and if we don't, we have to look at the data sheet, and here it is. It says E1 minus E2, well in our case it's E4 minus E3, the levels it's going to, and that gives us HF. So we'll find the frequency. Draw an arrow on the diagram to show a transition which emits a photon of a longer wavelength than the one that you've emitted. So we know a longer wavelength must mean a lower frequency, so it must mean less energy. So we've got to look on this diagram for an energy transition that's got less energy than that one. Take care not to immediately assume that if the lines are drawn close together that means that the energy transition is less, because it does say it's not to scale. So we've got to find the difference between different energy levels, and we're looking for a gap that's less than 0.33 times 10 to minus 18 joules, and then draw an arrow to show it.